So what problem we have here? So we have very many cloud services. In particular, some of them are just partially documented by web pages. They don't have anything but the ad hoc REST API. And we want to make rapid changes with infrastructure as a code. So we want to write a code fragment that sets up these cloud services all together and allows you to orchestrate them. And we have some kind of tech stack in here, because usually for cloud services, if the cloud providers provide any SDK, it will be in fixed language, usually JavaScript, sometimes Python, sometimes Ruby. And if we use like 8 cloud services, it's not unlikely that there will be no single language that is supported by all SDKs. Sometimes, in order to access some cloud services, we also need to support certain containers that provide the platform. And there is an option of documenting the cloud APIs in OpenAPI and generating code from that, but it is still poorly supported by vendors. A lot of OpenAPI spec files that you find on the internet are in different formats and not really the latest OpenAPI, and only partially conformant with OpenAPI spec. You can try SmartBear database, but unfortunately it's incomplete. So our goal is like full tech stack agility. So we use any language, any library stack, and easily replace them. In order to do that, we need to generate the cloud service bindings and combine best available microservices. So you can imagine a web application that uses Cloudflare for fronting the domain, for managing it, for DDoS protection, and then Mailgun for handling email, the Amazon S3 for storing the static assets, maybe Google Firebase for active dynamic assets. So a lot of different services. And most SDKs are not really that multi-platform. So we would like to move between them, because sometimes there is a service that just provides a better overall experience, right? And solution would be to generate the code for all the API bindings for different cloud platforms. And the source that we have would be from web documentation. So we need first to scrape the API documentation, and then put them in common format, analyze them, and generate the code, and retarget it to other languages besides Haskell, because we love Haskell, but other people may use other languages for their services. So issues we have here. The first and most important is that cloud APIs actually use the most complex calling convention known to humankind. It's like REST methods. Each argument has a different parameter passing convention, type conversions from text. In particular, if you look at the REST methods, you have so many different ways of calling the same function, right? Get, post, put, delete, patch. And then you can pass the variable to HTTP method by different ways. You can put it on request path on URL. You can URL and encode it as query parameter, right? Then you can add a custom HTTP request header like XAMZ transport encoding chunked. Oh my God. Like 5.3 bug reports on that and spent many hours. And you can just use HTTP cookie because everybody loves cookies, except that I think they plan to remove support for cookies in process, so maybe they will go away. But other things won't. So we have custom HTTP auth header. We also can pass arguments as HTTP request body. It can be JSON, and then it's nice because we can parse JSON, except that we don't really know what is its schema. Yeah, well, or XML, or some other format. God forbid, arbitrary text. Then we need type conversion from this JSON or other argument types into some sane types that you have in your programming language. In our case, Haskell, which are definitely not similar to JSON. So we have special strings that represent the VPCs or user IDs or timestamps or ISO 8601 dates, things. And usually in the web documentations, you only have examples of these values. So we use JSON auto type, which automatically types and provides you a data type declaration for JSON documents. I recommend that, but I will not talk too much in detail. It just parses the JSON and generates Haskell data type for each JSON. And that is the result. So after scraping, we look at different web pages for different cloud services providers and see how many calls in total we have detected there as in documentation, how many of them could be parsed. Sometimes it's better, sometimes it's worse, but it's generally resilient enough that we can fail for few calls. We may not be able to just directly use them. And the overall library code generator works because most of us do not use all the endpoints, especially with big and complex API like Azure, 5,461 calls. Yeah. Anybody knows them by heart? I don't think so. So this is a nice diagram of the implementation. It's a general sketch. So first we take the URLs of the web APIs, then we put them in crawlers. The crawlers scrape the web pages, and for each web page we have an extractor that basically iterates over the data on the web page. That we convert to CSV in a common format that is then parsed and analyzed by Haskell using JSON parser, using parameter description parser, HTTP request parser, and use example parser. And all together is put into the data structures that describe JSON types, parameter types, and HTTP request types. And that is together post-processed and then used for code generation. And when we generate code, we separately generate data types for input and output of each call, right? So arguments, all arguments together as a record, and the response. And then we also generate code for calling the function. We use servant for implementing the actual code. So, this is how implementation works in the first sketch. Detail will basically use these three modules first for scraping, then second for parsing and analysis, and third for code generation. Two of them are in Haskell. The first one is in Python because Python and tools like Scrapy library are the state of art for scraping just now. And you can also use Scrapy. That's relatively easy way to set up a scraping project, basically to download a set of web pages and just look with XPath for data. Luckily, most of this documentation conforms to a common format. So if you use Chrome driver, you probably see the same documentation as user does. If you don't use Chrome driver and you try just to pull the HTML files, sometimes you may not see it because most of the documentation, for example, for Azure is distributed as JSON and then formatted in your browser as HTML. And since this JSON format is not documented, we use HTML pages instead. XPath is the standard way of pulling content out of pages. We also sometimes use CSS selectors and regular expressions or JQ. JQ is basically JSON query language. And then for parsing and analysis, we break down the entire API call path into different segments that behave differently. There are constant segments and variable segments, for example. We use, of course, JSON type inference with union types, and we also parse core argument scripts with OptParse applicative to figure out how this, if there is curl script and basically a shell script that calls curl command, we can figure out certain parameters, how they behave better than from just API call path. The next thing is that we implemented entirely in Haskell as a monad stack for the code generation. That allows us to make it simpler. So we basically just push the code fragments, put the code fragments, and have a monad that manages naming and make sure that it's not redundant, and the logging and dependencies between the output files. We also use agile data format. So we basically use the common record format for most of the pipeline. So most of the pipeline does the analysis and then code generation. So we use the same technique as GHC used, which is using the common core language and put the data format that can be easily used without really understanding all the details of it, but is used across all the entire pipeline, right? So about retargetability, maybe we will talk next time because I think the time is running. So this is the example code fragment for Mailgun API. So we see a delete domain method. So you select, you see the first, there is a servant type that describes that there is first constant element of the path domains, then there is a specific domain name that is to be captured as a variable. Then there is basic authentication method, and then there is a delete call with the JSON result. With the JSON body argument and response. The arguments are described as the record Mailgun domains delete args. Here is mostly authentication and domain. Below there is the example call that basically uses servant to organize the call from the argument type. So the limitations here are generally it's quite some work to make sure that the code generation is bug-free. I'm not entirely sure we completed this part, but well, nobody does. Replicating bugs from documentation may also happen. We already know that some of these things needed to be fixed because basically the documentation didn't make sense at times. But obviously, if not many people use the endpoints, there is low motivation to fix the bug, right? Then there are companies that do not really provide even a REST call method documentation. They only provide a JavaScript SDK or Java SDK, in which case our approach would not work. But the number of such companies that do not provide the documentation of their web APIs is decreasing, luckily. And we really have thousands of API calls available within relatively short time, and we hope to expand on it on decreasing cost. So we easily scale to add new APIs to the processing pipeline. And we no longer depend on actual support from the vendor of the pipeline that may be only interested in JavaScript, right? Which is a little bit sad. So the running example of how we perform such an analysis in Haskell is that we have this record. It's simplified, so it doesn't contain all our fields. It's just a simple example, right? A record with description, amount, and date, right? Then we start by parsing it as CSV, and of course, parsing interface will fail. So this is a wrong interface in a way. We need to somehow record the errors. The typical way of dealing with that is to issue maybe error, but that is a wrong approach because that would not give us error message. So in our processing pipeline, we always use either that returns error message. But it would also be imperfect way because that means that we stop at the first error, and that's not what we want. You see, in the statistics that I've shown you before, only few APIs were completely handled and parsed, and that means that mostly there will be some incompleteness in your processing. If you have a big enough data set, there is bound to be error, right? So that would be a pretty opaque way because the first error would stop everything, right? And because of that, we basically return list of successful values and a list of errors, so that when our data set grows, we just show more errors. This is a simple demonstration if the likelihood of the error is of the order of 1 in 10,000, and you have million records to process, the likelihood that you will process an entire file is also below 1 in 10,000, right? So we really need this approach of always retaining a list of successes and a list of errors to scale to big data sets. There is no other way. So then we add the information, not just why something does not work, why the record cannot be processed, but also details like where exactly the record has been issued from, and where inside the record the issue has happened. And that really speeds up the debugging. We are not at the stage that we would automatically file reports for the problems with the analysis, but that is on the roadmap. And of course, it is a nice monoid, so you can easily build a monoid interface for the failures as the number of failures grow. Just keep them in a writing mode as a logging of all the problems that occurred, and just use the monad to return a list of successes, right? And in case there may be exception happening, you want to catch each issue and basically add it to the logging monad. You don't want really to have any kind of exception that breaks your processing in entirely. So examples of how we cannot do it, again, is head of empty list, right? Because head of empty list sometimes doesn't tell you anything if you have exception traits. And whenever there is actually a problem, we basically output entire record with all the additional information about it to locate the error. For interested people, it is profunctor. So the left argument is is contravariant, so it's logging argument. The right argument is the monadic result. And if you add the path to error failure, then you can also do it in JSON. It's also all the better. So I will skip that because I have a little bit more nice diagrams. So we actually classify the records by the type of errors and the severity of errors, and aggregate it on each run to estimate what are the most important problems in processing. We also use hierarchical data types to customize our core data type at each stage of processing. Maybe we'll skip that part. And I think because we are already about to finish, and I would like to hear your questions, I would just emphasize that we use standard data formats, and at each stage of pipeline, we are able to dump all the information and read it to facilitate the debugging. And here are the references, and I would love to see your questions.
Okay. Well, everybody, I encourage you to thank the speaker with a clap, please, and please raise your hand so I can bring you on stage to ask your question. Or if you can't raise your hand, then of course you can type your questions in the Q&A section. Any questions, anybody?
So meanwhile, I will comment on a comment of Yusuf, who noted the most complex calling conventions known to humankind. It's the truth. Yeah, it is sad truth, indeed. Because when I have experienced the pain of libc transition and few other ABI, application binary interface calling conventions, I always thought that would be less and less frequent when technology advances. Unfortunately, handling with the more and more complex calling conventions have been universally important over time, and that doesn't seem to be addressed by the current computer science. So I'm looking forward to young PhD students who will tell us how to design calling conventions better. We hope to release some of the generated code at the end of this year, hopefully. I really thought it would be like second quarter, but honesty does not allow me to say that it's realistic deadline. We still need some to do some more debugging for the code generation in other non-Haskell languages.
Okay. I think we will stop here because of the 10-minute coffee break. So Michał will be at one of the lounge tables to further discuss. So let's congratulate the speaker again. Thank you for your talk, Michał.
Thank you very much, and looking forward to see you in the lounge.